We have Josh Felmeden. He's talking about giving SL4 a native USB driver stack. And the topic of his talk is from zero to a native xHCI driver. So, Josh, stage is yours.
All right. So, hi, I'm Josh Felmeden from Capgemini Engineering in the UK. And this is how we ended up with a native SL4 xHCI driver. So, first and foremost, the current state of the project is available on our GitHub. And it can support mouse, keyboard, and touchscreen. And we really encourage you guys to go and have a play. It works on the MaaXBoard. Go and have a look, go see how it works. It's available there. So initially, we wanted to create a native USB driver specifically for the xHCI. We really wanted to create it with sustainability in mind, so that in case anything was to change, we'd be able to keep that updated. And we also really want to help lower the barrier for entry. As I've mentioned multiple times, it's quite hard to get into SL4. And drivers for useful protocols such as USB would really help to encourage and facilitate the use of SL4, and then to write an experience report about it. So yeah, I'm part of the team that developed the developer kit. I didn't personally develop it, but I joined after it's finished. So the previous work package was focused on creating extensive driver support at the SL4 dev kit GitHub, and that uses modified U-boot drivers. It also has got a really wide range of platforms to support and has a lot of devices, so yeah, USB, HDMI, something like that. It's really easy to extend the library as well, and there's a lot of notes on how to get up and running and how to extend the library. So the focus today is specifically on an xHCI driver, and you might ask, why didn't you just use the ones that have been provided before? And basically it's because the U-boot drivers that it relies on have no interrupts, so it's all just polling, which is really quite not as performant as device-driven drivers, and the licensing issue. So U-boot is GPL licensed, which is not permissive as other licenses, such as BSD. So the current development we've got offers an xHCI driver without the above. So we looked at a wide range of USB drivers because writing one from scratch would take a really, really long time. So we wanted to pull one in. So we ended up on NetBSD. We used NetBSD because it boasts portability. So the generic code, it can support a wide range of hardware. It's also BSD licensed, so that reduces the issue we have with licensing. It's updated often, so it'd be easy to keep up to date and ensures safety. Interrupts, yeah, uses them, check. And it's a base from which to pull other drivers or services in the future. So if we want to go down the file systems mass storage route, we could do that. So a quick background on xHCI and what it is. It's just a protocol for communicating with USB devices. It's an advancement over those three, which supports all the speeds. But xHCI supports all those speeds, and there's no need to explicitly include drivers to support those. It does it all. And it just describes the basics between software and the host controller. So memory setup, data structures, so rings, all that kind of stuff, memory maps, and direct memory access, and how they should be set up and look to the controller. And we specifically focus on that bit. That's the sort of area that we create for. So we started working on cam keys. So the first challenge for us was interfacing with the hardware. The team that I was part of, we didn't have any experience with SL4. We had some, obviously the previous people who worked on it, they were around to help, but we wanted to initially interface with hardware. So the first step we did was we compiled NetBSD, and we traced the initialization of the xHCI, and we just read the first input-output read and write. So for example, on the MaaXBoard, it first reads out the version of the xHCI. So we just wanted to hard code the address in, make sure we can do it, and we did it. So once we'd done the hard coded register addresses, we could work out sort of the changes we need to make to the driver to make it compatible with SL4 and cam keys. So once we did that, we initialized a host controller, set up all the DMA, and it was up and running. We were able to initialize the host controller. And then we wanted to move to Microkit, or previously Core Platform. So that was a whole new system description language, which took a bit of time to readjust, but actually it was a really positive experience. Cam keys, I'm sure you've heard, is a bit of a beast, but the Microkit is the transition was very, very painless. The biggest challenges that we found were there's no standard libraries yet. So we were able to import external minimalist replacements functionality, so your print statements, your memory handling, and there's no DMA library, so cam keys comes with DMA library already there. So we had to create a simple replacement for that. And finally, there's no build system. So yeah, cam keys comes with CMake Ninja build. So we opted for a simple makefile because all of the examples that we've seen on Core Platform, Microkit rather, use the makefile. So we use something similar. And so this is the basic system architecture that we've got. So we've got a central driver. so the main protection domain, and that handles all of the initialization. That communicates with the hardware via the MIO. That call itself calls into a hardware interrupt, which then itself calls into a software interrupt, and this is to allow the hardware interrupt to occur while the software interrupt is occurring, and those call up into the USB class drivers, so be that their keyboard, mouse, whatever it may be. And the task thread over there is something that NetBSD uses that we haven't implemented because that would be something for hot plugging, and as has been mentioned a few times, the systems are static in SEL4, so that's not really necessary, but that would be the, if it was there, that would be there. So once we initialized the actual host controller, we were able to see some devices. So we started with a keyboard because it would be quite straightforward to get a proof of concept. You type on the keyboard, can you get some characters to the screen? And it uses a human interface device as a base, which would be used by other things like mouse. So one of the issues we had was hard-coded functions. So with USB, obviously, it sets up a transfer, tells the host controller to go, and then it comes back to a callback. And initially, that was hard-coded to avoid various memory issues. So between the core driver protection domain and the software interrupt protection domain, there's an issue because it uses a lot of function pointers. NetBSD uses a lot of function pointers because it's expecting to be used as an OS, so it's all expected to be in the same memory regions. So if it's initialized a callback function at address A, and then it goes to sleep, and then the software interrupt comes in, and it calls it back at address A. Obviously, that doesn't exist in the context of the software interrupt. SL4 flags that, and then it crashes. So there are two possible solutions that we found to this. First was to initialize a master protection domain that handles all the functions. So, and then we'd have the driver RPC up into it, and then when the interrupt comes in, it RPCs into the callback. But the issue we had with this, and we chose not to go with this, is because when a driver RPCs up into the callback, it's operating at the higher priority than a software interrupt, which can have quite an impact on performance. So instead we opted for a context switch. So very simply, at the initialization, the two protection domains communicate and they tell each other, here are the different memory addresses that I'm going to use. And then it just does a check, is it A? If it's A, then it's this equivalent callback, and likewise for C. So now we had the keyboard added, we wanted to add further functionality, because at the minute it was just a keyboard, so basically just a keyboard driver. So we added a mouse. So conceptually they're very similar, they're both human interface devices, and so it had the same fundamental layer. So that was quite easy to add, we just had to include the mouse setup files that NetBSD had. And likewise with the touchscreen, if you squint really hard at a touchscreen, it's kind of like a mouse. It just has an extra form of setup. It's got a Z direction as well as the X and Y. So we were able to make use of the generic code for the mouse and add the touchscreen on top. So the next issue that we ran into was that when you probe the bus for drivers, you have to explicitly say what device is being attached. So it's quite inflexible at the minute. You have to modify the code and recompile the entire program. When switching between devices, you couldn't have the same one as keyboard and mouse. So we then introduced the NetBSD's auto configuration. So that makes use of something called a match function, where it looks at the device description when you probe the bus, and it says which device is going to assign it to. So it has a big list of devices for reference created at NetBSD kernel compile time, which obviously we don't have because we're not actually compiling a NetBSD kernel. But we can just extract the list and trim down any unnecessary devices that we don't need, so any non-xHCI or any non-implemented devices, and that avoids the explicit setup requirement. It also allows our driver to determine the best match automatically for each device. So that's where the project is at the minute. So linking with other projects, so how would you use this device driver currently? So we're working on extracting the key press, again, because the keyboard's very easy to sort of set up and proof of concept. Extracting key presses using channels and exporting to other projects. So that's Lucy Parker's Ethernet driver. We're working on and have actually managed to combine them together, typing on a keyboard and then sending the key presses over Ethernet, and just sort of proves compatibility with other SEL4. Excuse me. Other SEL4 drivers and how to interact with our driver. So in the future, something that we're working on at the minute is mass storage. So that'll be the first device that we are incorporating. It doesn't have the human interface device fundamentals, and it requires a few more complicated concepts like file systems and things like that. We'd also like to update the dev kit. So the dev kit is currently exclusive for the MaaXBoard. MaaXBoard cam keys, and we'd like to port that across to the Microkit. We'd also like to look at bringing in a libc, like a standard library for Microkit. And once again, driver's available at this address. Please have a play. Give us any feedback. And that's all I've got. So thank you very much.
Okay, thanks very much, and cool for staying on time. So we have 5 minutes for questions.
I think you answered it in the talk, but I might have missed it. Is this all still a single-threaded driver?
Let's find there's the architecture. So a lot of the functionality is clumped into the main protection domain at the minute. We're looking to separate it out into the class drivers, so that obviously when it does the keyboard or whatever device it is, it'll call into the protection domain for that device. But at the minute, it's very much clumped into the driver or the software interrupt protection domain.
But I guess to reframe my question, the NetBSD code has a lot of task stuff in it.
Yeah.
And you're saying that you didn't need to have that for HID class devices yet?
No, we just sort of removed it and just called it rather than tasking it. We just called it single-threaded.
Okay, it's good to know. Thank you.
Okay, I'll first preface this question with I'm not familiar with USB at all.
Okay.
But I don't quite understand why you have multiple interrupt handling components and why the driver doesn't take responsibility for that. And so if you could maybe talk a little bit about what the key differences are between the software interrupt handler, the hardware interrupt handler component, and the driver as well.
Yeah, sure. So as part of the initialization step, the driver's it'll queue some transfers and then it will be interrupted. If I try and combine that into the same, into the same protection domain, it will just sort of deadlock because it's waiting for things to happen. So, and then the reason why I've got a hardware and a software interrupt is because sometimes it comes in and schedules a hardware interrupt. I guess I could actually combine the two. I think about it, hardware and software. But yeah, the minute is so that the hardware interrupts can trigger, and then they can acknowledge the hardware interrupts, and it will schedule software interrupts via the notification.
You get that anyway just using SEL4 notifications as the interrupts.
Yeah, now I've said that, I think I could probably combine hardware and software, but the yeah, software and driver, they had to be separate just because when I was using them, it would just deadlock between the two. But yeah, hardware and software, I think I probably could separate combine into one.
Okay, thank you.
Hi, two things. One, if you have thoughts on Isocrates USB class stuff and what semantics you'd map that to in the system, and two, if you encountered the rump kernel stuff in NetBSD and if that made your life easier in any way.
Can you do the first one again? Sorry, I misheard that.
Sure. So with USB devices, there's the whole isochronous class of devices. So like, say webcams or whatever, that have some allocated bandwidth for streaming stuff. Wondered if you encountered that and if you had thoughts on what you would want to what semantics of the underlying system you would want to map that to expose such devices.
I have encountered those, but we haven't actually come around to implementing them yet, though. So I haven't really thought about it that much, to be honest. It looked quite scary. So I haven't really thought about that yet. But I have seen them, and the code exists in NetBSD. It's all there, obviously. But I haven't looked at that yet, no. And what was the second thing?
Yeah, the eternal re-implementation of drivers and all the duplicate effort there across all the different systems kind of makes me sad. And in NetBSD in particular, there was the rump kernel interface, which was designed originally to try to make that the lives of people such as yourself doing this work easier, to make portability easier. I was wondering if that was something that you had encountered in porting stuff from NetBSD, and if that had made your life easier in any way.
That isn't something I'd incorporated. That's something that I'll make a note of and go back and feed that back. Thanks for that. Wasn't aware of that. Thank you.
Okay, any more questions?
So this question may not be the USB related directly. When you do this, do you know if SEL4 can handle the RQ sharing? So multiple devices use the same RQ pin.
Can handle what, sorry?
The RQ sharing.
The accuracy, as in?
RQ sharing. So multiple devices share the same RQ pin.
Sorry, I can't. IRQ sharing. I see. So because because of the sort of structure of xHCI is as like a star network, it all comes in through the same IRQ. So if you have like multiple devices plugged into a hub, it all shares the same xHCI single IRQ. So it's like 32 on MaaXBoard. So if you have a mouse and a keyboard plugged into a hub in the same port, it all comes through the same IRQ, and then the xHCI protocol dictates what happens from there. So it's all sort of software related, but it all sounds the same IRQ.
Okay, then thanks again, Josh, for the interesting talk.
Thank you.